Ever need to check if a network is robust, fully connected, and loop-free? Graph Valid Tree is a Pattern Mastery 100 favorite, used by Google, Apple, and Meta to test your core understanding of graph cycles and connectivity. Over 30% of candidates get tripped up on edge cases like cycles or disconnected graphs. Master this and you'll breeze through network design and validation problems. Let's break down Graph Valid Tree with a basic method, ensuring you can confidently tackle any connectivity or acyclicity question in interviews. Given n nodes labeled 0 to n1 and a list of undirected edges, determine if these edges form a valid tree. A valid tree is connected. There's a path between every pair of nodes. Acyclic, no cycles. Integer n, number of nodes, list of undirected edges. Boolean, true if the graph forms a valid tree, false otherwise. Imagine verifying a computer network or electrical grid, no redundant paths, cycles, but every device must be connected. An interviewer might ask, how would you validate that a topology is a tree and not a forest or a cycle? What's tricky? Must check both connectedness and absence of cycles. Some solutions miss edge cases, disconnected graphs, or graphs with exactly one cycle. For a tree, exactly n1 edges for n nodes. Edge count check, if there aren't exactly n1 edges, it can't be a tree. Connectedness check, use DFS/BFS to visit all nodes from node 0. If you visit all nodes, count equals n, the graph is connected. If any node is unreachable, it's disconnected. Cycle check, if any edge leads back to a previously visited node, not the parent, it's a cycle. Edge count shortcut, if the edge count is correct and you visit all nodes without cycles, it must be a tree. Let's clarify. Using Union-Find, disjoint set union, DSU, is also common. Detects cycles as you add edges and checks if all nodes are ultimately connected. Edge cases. Disconnected components, not a tree. Extra edges, more than n1, must have a cycle. Single node, n equals 1, edges equals 0, valid tree. Edge count, return false if len edges equals n1, DFS/BFS. Build adjacency list from edges. Start from node 0, mark nodes as visited. If during traversal, revisit a node that's not the parent, it's a cycle, return false. After traversal, check if all nodes are visited, connected. Return true if no cycles in all nodes visited. Let's try to implement it using solution 1. Time complexity, O(n plus e). The concept discussion. To confirm an undirected graph is a valid tree, we need two things. 1. No cycles, and 2. Everything is connected. There's a super helpful shortcut here. For an undirected graph with n nodes, it can only be a tree if it has exactly n1 edges. So we first check that. If it fails, we instantly return false. If it passes, we then run BFS from node 0 to verify connectivity, meaning we can reach all nodes. If BFS visits all n nodes, it's connected, and because we already confirmed the edge count is n1, it must be a tree. This function first verifies the edge count rule for trees, then uses BFS to ensure the graph is fully connected. This is the fast gatekeeper. A tree with n nodes must have exactly n1 edges. If there are fewer edges, the graph can't be fully connected. If there are more edges, there must be a cycle. So if this check fails, we don't even need BFS. Next we build an adjacency list so we can efficiently explore neighbors. Since the graph is undirected, every edge connects both ways, so we add v to u's list and u to v's list. Now we start BFS from node 0. We create a visited set to avoid revisiting nodes, and a queue to process nodes in BFS order. Marking 0 visited right away ensures it won't be added again. This is the BFS engine. We repeatedly pull a node from the queue, look at all its neighbors, and push any unvisited neighbor into the queue. By the end, visited contains exactly the set of nodes reachable from node 0. Finally, we verify connectivity. If BFS visited all n nodes, the graph is connected. And since we already confirmed there are exactly n1 edges, that combination guarantees the graph forms a valid tree. And that's how this algorithm works. It first checks the tree edge rule that edges must equal n-1. Then it runs BFS from node 0 to confirm every node is reachable, proving the graph is connected and therefore a valid tree. Efficient, simple, and elegant. Let's test our function using this input. We have n equals 5 nodes, labeled 0 through 4, and these edges define how the nodes are connected. First, the code checks a key tree rule. A valid tree with n nodes must have exactly n1 edges. Here, n1 equals 4, and we do have 4 edges, so we pass that quick filter. Next, we build an adjacency list and run a BFS starting from node 0, marking nodes as visited as we go. From node 0, we can reach node 1, 2, and 3 directly. Then from node 1, we can reach node 4. So by the end of BFS, every node 0, 1, 2, 3, 4 gets visited, meaning the graph is fully connected. And since we already confirmed the edge count is n1, that also guarantees there's no cycle. Connected plus no cycles equals exactly what a tree is. And that's exactly what our program outputs, true, matching the expected result. The output makes perfect sense because all nodes are connected in one clean structure with no extra edges creating loops. So, our implementation is correct. The algorithm verifies the tree property by checking edge count and confirming connectivity with BFS, efficient and accurate. Let's try to implement it using solution 2. Time complexity. The concept discussion. A valid tree in an undirected graph must have no cycles and be fully connected. We again use the key rule. A tree with n nodes must have exactly n1 edges, so we check that first. Then we use Union-Find, disjoint set, to detect cycles as we connect nodes. Union-Find groups nodes into components. When we process an edge, u, v, we try to merge the two components. If u and v are already in the same component, adding that edge would create a cycle, so it's not a tree. If we successfully union every edge without a cycle, then with the edge count check, the graph must be a valid tree. This version checks the edge rule, then uses Union-Find to ensure no cycles appear while connecting all nodes. This is the fast filter. If the number of edges isn't exactly n1, it can't be a tree. Too many edges means a cycle exists. Too few means it can't be fully connected. Now we set up Union-Find. Initially, every node is its own parent, meaning every node starts in its own separate component. The rank array helps us keep the structure balanced so operations stay fast. Find answers. Which component does this node belong to? It climbs up to the leader, root. The extra step here is path compression. After finding the root, we point nodes directly to it. That makes future lookups much faster. Union tries to connect two nodes by merging their components. If they already share the same root, that means they're already connected, and adding this edge would form a loop, so we return false to signal a cycle. Otherwise, we merge the smaller rank tree under the bigger one to keep things balanced, and return true to show the union succeeded. Now we run through every edge and union its endpoints. The moment union returns false, we've detected a cycle, so we immediately return false, not a tree. If we successfully union every edge with no cycle detected, then we return true. Combined with the earlier n1 edge rule, that guarantees the graph is connected and cycle-free, in other words, a valid tree. And that's how this algorithm works. It first checks the required edge count n-1, then it uses Union-Find to merge components edge by edge while detecting cycles, and if no union ever forms a cycle, the graph is a valid tree. Efficient, simple, and elegant. Let's test our function with n equals 5 nodes, 0 through 4, and these edges, 0, 1, 1, 2, 2, 3, 1, 3, 1, 4. Each pair means there's a direct connection between those two nodes. Right away, the code applies the tree rule. A valid tree with n nodes must have exactly n1 edges. Here, n1 equals 4, but we actually have 5 edges. And that's already enough to conclude it can't be a tree, because having extra edges guarantees there's at least one cycle somewhere. So the function returns false immediately, without even needing to run Union-Find. And if we did think about it structurally, you can see the loop 1, 2, 3, 1 forms a cycle because edges 1, 2, 2, 3, and 1, 3 connect back around. And that's exactly what our program outputs, false, matching the expected result. The output makes perfect sense because the graph has too many edges and contains a cycle, so it cannot be a valid tree. So, our implementation is correct. The algorithm quickly rejects non-trees using the n-1 edge check, and it would also catch cycles via Union-Find when needed, efficient and accurate. Alright, quick recap to wrap up graph valid tree. We're given n nodes and a list of undirected edges, and we're checking whether the graph forms a valid tree. A true tree has to satisfy two rules at the same time. It must be connected, meaning every node is reachable, and acyclic, meaning there are no loops. The key insight is that a valid tree always has exactly n-1 edges. If there are too few, the graph can't be fully connected. If there are too many, a cycle must exist. So the edge count becomes the fastest filter. Then we confirm the rest by verifying connectivity or detecting cycles during traversal. The plan was, first check that the edge count equals n1. Then build an adjacency list so we can traverse efficiently. After that, run DFS or BFS starting from node 0, and make sure we end up visiting every node. During traversal, We marked nodes as visited to avoid repeats, explored neighbors to cover the whole graph, and if using DFS, we tracked the parent so we don't mistake the back and forth undirected edge for a fake cycle. The solution ran cleanly on LeetCode with no errors. We validated that it correctly rejects graphs with the wrong edge count, detects disconnected components, detects cyclic structures, and all test cases passed. The main takeaway is simple. A tree is connected plus acyclic. The N1 edge rule is the quickest filter, and then traversal confirms everything else. Master this, and graph fundamentals start feeling automatic.